Hello and welcome to Mastering RTOS Debugging Techniques. I'm Jacob Beningo, and I'll be your host and lecturer for today's session. Now before we dive in, just to give you a little bit of background about myself, I'm an embedded software consultant who has been working in the embedded systems industry for more than 15 years. I've had the opportunity to design products based around little 8-bit microcontrollers, 16-bit microcontrollers, and of course 32-bit microcontrollers as well. I've developed software that use just simple super loop type of scheduling techniques all the way through the most modern real-time operating systems. Every year I get the opportunity to interact with a number of companies and also engineers at different types of events such as these webinars, at events such as ARM TechCon, Embedded World, and the Embedded Systems Conference, where I give different talks on different techniques that can help developers improve their development cycle and also improve the robustness of their embedded systems. Now, one of the topics that I've noticed from talking with a whole bunch of different companies and engineers is that debugging is becoming a major issue for a lot of us as the complexity of our software becomes, well, more complex. So what we're going to do today is dive into some different techniques and even the problems that we can encounter when developing software around a real-time operating system. Now, before we dive into the details, I'd just like to try to get your attention and to look at this slide. You can see here that I didn't pull this webinar together all on my own. There were actually a couple of other companies involved to make this webinar happen. They shared not only their knowledge and expertise, but also helped get the attention of attendees to let you know that there was an event happening today. So if you ever go out on social media, if you just take a moment to thank Keil, NXP, Percepio, and Embedded Related for everything that they did to help support this webinar and bring it together, I would greatly appreciate it, and I'm sure that they would as well. A couple of notes before we do get started. I just want to let you know that there are individuals from each of these companies on the chat window right now as I speak. At any time, if you have a question about something, whether it's related to a product or just general concepts about debugging techniques, please feel free to use the question box in order to ask your question. We'll get an answer to you as quickly as we possibly can. There will also be some time set aside at the end of this webinar for you to also continue to ask questions, and I'll hang around for a while afterwards as well. Now, the purpose of today's webinar is really to talk about real-time operating system debugging techniques. This is going to be the techniques and tools that we need as embedded software developers to be able to efficiently debug our systems. Now, there are, of course, a lot of different topics that we could cover today, but given that we only have about an hour, I've chosen a couple of topics that I think will be of most interest to the attendees. Now, some of the topics I'm going to cover today, I'm going to start out by talking about, in general, debugging, some of the issues that we have with it. I'm also going to explore some of the different pieces of hardware and the different ways that we can debug an embedded system in general. Once we talk about those different techniques, I'm going to dive in and talk about specific problems that developers have when using a real-time operating system and the types of and how we know that we actually have a problem. Then I'll talk you through how we can set up an event recorder. Once we set up an event recorder, we can actually go through and trace our real-time embedded software and see what's happening in our system moment by moment. Once we've gone through and talked about that, I'll talk a little bit about how we can size our stack properly for our threads in our application. And then I'll talk about some general best practices, just a few to give you a little taste of things that we should be doing in order to minimize our chances of having bugs in our system. Now, just like with most of my webinars, I like to take a hands-on approach. So what I did was I did get a development kit, an NXP K64 Freedom board. I'm going to be using the Keil MDK 5, the latest version, which is 5.24. I have a simple example that I put together that has a couple of semaphores, a few threads that interact and blink some LEDs. Those examples can be downloaded from my website at www.beningo.com. And then I've also gone out and gotten the Percepio Tracealyzer tool, which we'll use coupled with Keil to be able to get event data and then go in and visualize and see what's happening in our embedded system. So one thing to keep in mind is that I will record this and it will be made available to you shortly after the webinar. So if you want to go back later on and actually run the examples in parallel with the webinar, you should be able to do that without any problems. Before I get into the actual demonstrations, I'm going to cover a lot of the discussion on what kind of problems we can have, the hardware, give you some ideas of debugging techniques. So most of the demonstrations are going to be towards the end of this webinar today. As I travel around the world talking with companies and engineers, one of the things I've noticed is that one of the greatest development challenges that we face as embedded software developers and as companies is the amount of time that we spend trying to debug our embedded systems. Debugging is a huge issue, and it's an issue for a number of reasons. One, developers tend to get a little bit stressed out as they're trying to debug their software. Sometimes bugs aren't simple and they can be extraordinarily complex. Complex things, especially under a tense deadline where we're trying to get to market as fast as we can, or maybe the deadline has already come and gone, it can add a lot of stress and pressure to people. And when that happens, of course, it's going to take even longer to debug. Now, that is, of course, not the only issue with, debugging is just stress. A major issue is that debugging costs a lot of time and money. And you may consider, well, does it really? From the engineers that I've talked with, I get ranges of how much time is spent in the design cycle debugging software, ranging from 40% of their time all the way to 80% of their time debugging software. Given a typical development cycle of 12 months, that means a developer could be spending at least 5 months out of the year debugging software. This, of course, might be fine if you love debugging, but if you're someone like me who likes to really design everything and doesn't want to spend 5 months out of the year pulling his hair trying to figure out how to solve a problem that should just be working in code, you're going to want to become more efficient at debugging your systems. And that is exactly what we're going to be talking about today, is what tools are necessary in order to make debugging extremely fast and to make it a more scientific approach. A lot of times developers, even today, when they're debugging their system, they don't really know what's happening in the system, in their software, how the flow of execution is occurring. What happens is that they hit run button on their code, and then they just kind of cross their fingers and they hope that it actually does what it's supposed to. Heaven forbid something doesn't work the way that they expect, at which point they just have no clue and they start maybe throwing some printf statements here or there, maybe blinking some LEDs as they try to figure out what's actually happening. Some of the techniques and tools I'm going to show you today will actually allow you to scientifically and from an engineering standpoint, get data to analyze to figure out what's actually wrong with the system, rather than having to play the guessing game. Now, before we talk about the techniques, we should talk about some of the hardware that we're going to want to have available to us. First of all, I'm a microcontroller developer, so pretty much everything I'm going to be talking about today is based around debugging techniques for ARM Cortex-M processors. There's a couple of pieces of hardware that we want to make sure that we have. First of all, we're going to want to make sure that we have a debugger that's capable of doing some basic trace. Pretty much any debugger that has serial wire debugging capabilities nowadays is going to at least allow us to be able to do some type of tracing, at a minimum some statistical profiling based on the PC counter. So we want to make sure that we have a good debugger associated with it. The faster the debugger, of course, also means the more events we're going to be able to get off of the system as well. What you'll notice is that if you're using the K64 Freedom board, it does have an OpenSDA debugger on board. We can install JLink software on it so that we can get tracing capabilities. But because the debugger comes with the development kit, it's not a high-end debugger. So what you'll find is that it runs relatively slow. You can still do event tracing, but it's not going to have the throughput that you would get if you purchased, a $300 or $400 debugging tool. So we want to make sure that we have a good debugging capability with us, like a debugger. We also may want to be aware of some of the capabilities that the Cortex-M processor has associated with it for debugging and tracing. First of all, most microcontrollers that I've seen have a serial wire viewer associated with them, or at least can do serial wire debugging. This seems to be a very common interface, but it is optional as part of the IP, so you just need to make sure that your part actually does support it. And serial wire viewer does allow us to get some basic information serially out of our microcontroller, so we can do some things like printf. We might be able to set up an ITM port to be able to get a little bit faster data out as just a simple example. We also might have something like ETM tracing. This is going to allow us to actually do instruction tracing. Typically this has 4 extra data lines, and I'm going to talk a little bit about the hardware interface here in a little bit. And then we also want to make sure that we have DAP, which is the debug access port. We can use this hardware to help accelerate the event data that's being sent over to the debugger. Now, just like with any microcontroller, we're going to have potentially a couple of different interfaces that we can use in order to actually access and program and get debugging information from the part. There's a couple of different debug interfaces. Now, on the right-hand side here, you can see there's two different types. One is our typical 10-pin JTAG that many of us are used to. As part of this, though, we also have our serial wire debugger. We also have our serial wire clock. And you can see here this SWO, which is another serial wire output that can be used with the system viewer. A lot of the ARM parts are going to have serial wire debuggers built into them by default. And that's really probably the most common interface I think that I use when I'm going to be debugging an ARM-based microcontroller. But there are also, support for things like the typical JTAG that we're all familiar with. If we want to do any type of tracing with the serial wire debugger, we want to be able to get access to that SWO line. That is going to allow us to get some extra data output as part of the debugging, but it isn't necessarily required. We can just use a standard serial wire debugger pins. But usually it's just a single data pin. It's limited to approximately 2 megabits per second. So yes, we can get some data, but it's not exactly going to be the fastest interface that we could necessarily interact with. Another one that we could be using for debugging, which I don't see used a whole lot, unfortunately, it should be really used a lot more, is going to be the trace port interface. So typically ETM connector is what we would expect to see. So it's this 20-pin connector, and the thing that really makes this thing special is that it has 4 data pins and a clock. So you can see here we actually have four separate data lines that we can use in order to have separate channels and really be transmitting a lot of trace data off the processor at a given period of time. A lot of times this is going to be used for individual instruction tracing. So if you're doing something that's safety critical application where you need to go in and validate every single instruction that's being executed and actually see that, that is where you're going to want to use one of these ETM devices that has the full trace capabilities associated with it. Now, we all know that there are a lot of different ways that we can debug an embedded system. Some of the ways that we used even back on the 8-bit microcontrollers, where we would set in a basic breakpoint, where we double click on a line of code that we wanted execution to halt on. We'd set the breakpoints, get to that, and maybe we'd step through our code. Maybe we'd go and do something simple like setting up a variable to watch. Maybe we set up an expression. Probably a technique that most of us are familiar with is printf or using assertions, where we can just printf occasionally throughout our code. And if we happen to, we can actually log that data and then review it a little bit later. A lot of times printf isn't a great way though to debug a system, at least using the old 8-bit and 16-bit techniques where you're shooting it out of UART. Printf tends to be a blocking function call. So what ends up happening is that you're actually stopping and interfering with the execution of your real-time application. Now, there's a lot of newer techniques that are becoming available that a lot of developers, at least that I see, aren't aware of or that they don't use. One is using serial wire viewer doing statistical profiling. And what statistical profiling can do is, as you execute your code, it can actually occasionally sample the PC counter, the program counter, to see where the code is actually at. And what happens is that as it collects this data with a timestamp, eventually it can get a general feel for what percentage of execution time is being spent where. So if you have a function that's blinking an LED, you may find that, for 1% of the time, your code is going to be found when it samples a PC counter inside that LED blinking code. Or maybe you're finding that 50% of the time is in some error handler or communicate in some type of serial communication handler or something like that. But the cool thing about this is that a serial wire viewer will allow you to get some statistical data that approximates to get you a feel for how the system is actually behaving and where most of its time is being spent. The technique that we're going to be talking about probably the most today is actually going to be system tracing. And this is where we're setting up using a serial wire debugger actually, and we're just streaming trace data. So events that happen in the system, we're going to stream out of the system. So this could be when a task is initialized, when a task starts executing, when a task becomes ready to execute. Maybe there's data that we want to be able to send out. We can do that as well. So that's an example of the type of tracing we're going to be looking at today. Maybe when a semaphore is acquired or when it's given back. Those are going to be the system type of events that we're going to be looking at. Or maybe even if memory is being allocated from the heap. There's also other types of tracing that we're not going to look at today, which are things like instruction tracing, where we're looking at the individual instructions that are being executed and also looking to see which branches were being taken and what percentage of the code coverage we're getting. That's another type of tracing that we're not going to talk about today. We're going to focus in on data tracing and task tracing to see what our real-time operating system is doing, what threads there are and how they're interacting with each other, and what interactions are there with the RTOS objects as well. Now, there are several different ways that you can debug a system, a couple of different methods. The first is invasive debugging, and these are the type of debugging techniques that we're most familiar with. Setting a breakpoint, single stepping, maybe doing a reset, a resume, setting data watch points, accessing internal registers. These types of interactions with our embedded system break the real-time performance of the system itself. So what you'll find is that the system, while you have the debugger attached, may behave one way, and then when you remove it, it could behave completely differently. Now, the techniques that I prefer to use are going to be more non-invasive debugging techniques. This is where the debugging capabilities have almost no effect, if any, on the real-time performance of the system or even on the program flow. So what you'll find is that there are things like on-the-fly memory accesses, things that can happen in parallel with the code still executing, things like instruction tracing and data tracing, even system profiling. These types of techniques, when using the trace tools, have been designed. There's hardware on the microcontroller that takes care of monitoring these events in these systems that then make it so that it doesn't interfere with the flow of our application. Non-invasive techniques won't affect our real-time performance, which is why I prefer to use them. I don't want my code execution behavior to be changing once I'm done debugging my system. Non-invasive trace debugging can provide us with a lot of useful information. We can generate debug events. So this is where we get a debug event such as, hey, a data watch point was triggered, or hey, we want to halt the processor, or generate some monitor exception or something like that. Whether we're starting or stopping tracing, we can get this information. We can actually do data tracing, where we generate data trace packets that we can compare and match, try to match them to values or data addresses that we're interested in looking at, or even PC counter, the program counter values. We can sample the program counter and occasionally sample to see what's the value of it and provide a timestamp, and then that allows us to go back and do a statistical profile of how our system's actually executing. Remember, just a few years ago, we didn't have the capability to even see any of this. We literally just crossed our fingers and kind of hoped that the software executed the way we thought it should. And of course, crossing your fingers and hoping for the best really isn't going to get you very far in the engineering world. But we have that ability now to be able to determine our execution path and estimate how much time is spent in each function using the sampling of the program counter. I think probably profiling is really good. We can set up counters and then generate trace packets and collect that information at periodic periods of time, and even do exception tracing now, where we generate a trace packet when an exception actually occurs. We can send that over ITM and provide a great level of detail into the timing of how these events and exceptions are occurring. We even have the ability to decide, do we want to see all these events that are occurring in our system, or do we only want to focus in on a small set of them? We have the ability to look at every single event that's being generated by the RTOS, or maybe I just want to see the error exceptions. It's really up to us as a developer and how we set up our code. And I'm going to talk about that a little bit when I walk through the demonstration. So now that we have a basic understanding of the hardware capabilities, what's available to us now as a developer, it'd be useful to start to understand the problems that we could find when developing a real-time application with an RTOS. This slide lists several possible issues that are fairly common for developers to encounter. The first is that you create your application, you have multiple tasks or threads. As you start to develop each one, the thread works fine by itself. It doesn't seem to have any problems, but as soon as you try to integrate it into the entire system, sure enough, something goes wrong. So this is going to tell you that, yeah, there's some problem with the way that your system's synchronizing. There could be something more going on here. We may find that, hey, you know what, my real-time operating system, the performance of it is really slow. It's not behaving the way that I expect it to. Now in RTOS, a lot of times people who come from the bare metal world will say, oh, an RTOS has so much overhead, they're horrible, you shouldn't be using them, super loop forever kind of thing. But the fact is that most good RTOSs use well less than 4% of the idle time of the CPU. In fact, probably 1 to 2% is a very good rule of thumb to use. So the fact that a system seems to be performing slow is probably not the real-time operating system. It's probably the way that we've designed the system. And it could be a number of potential issues that we're going to be talking about here in just a couple of slides. Another issue is that the system locks up, or maybe it sometimes doesn't respond at all. In these particular cases, maybe you go and you push a button or a touch screen or something, and just nothing happens. You feel like you're using a Windows PC or getting the pinwheel of death. The system just isn't responding the way that it should for it being based on a real-time operating system. I've worked on real-time operating systems where I've gone to maintain code, and the system was just brittle as can be. Making very minor changes to the code seemed to cause really strange errors to occur. Different areas of code broke. Places in code broke that I didn't even touch. And when you see a system that's very brittle, it starts to give you a hint that, you know what, there could be a more fundamental underlying problem with the system. How do you find that problem, though, is a completely different matter that we'll be talking about. You might even see random variations in the output timing of your threads. You may find that you can't consistently get the right timing for your system. So this could be potentially a big issue. Sometimes maybe data is being corrupted, or you're getting the wrong output value. And then, of course, there are random crashes or hard faults where your system is executing the way you expect it to, and all of a sudden, bam, you're in some type of error handler. The error handler gives you some nonsensical thing. You can't figure out what is actually going on. You've hit some type of issue with the system, but you don't know what it is. Now, it turns out that there are generally 3 or 4 different possible problems when you have an RTOS designed application where these problems can be occurring. First, your system could occasionally be experiencing thread starvation. And thread starvation occurs when a low priority thread is rarely executed due to higher priority tasks always using the CPU. Now, one of the things that I did was I created a couple of sample applications, and then I generated some trace under these similar types of circumstances. And what you see here on the left-hand side is an example of thread starvation. You can see here we have some, the priorities actually go from left being low priority to higher priority on the right. You can see here we have some ISRs firing, a couple of different sensor tasks that are being executed. You can see here this is the time that the task is actually executing. And these hashed mark lines here show that, hey, this task is actually ready to execute, but it doesn't start executing until right here. Now, as you can see here, I've highlighted a thread here. There is this task here that, as you can see, obviously is not getting enough CPU time. It was ready to execute its code way up here, and it had to wait all the way till down here before it actually got access to the CPU. It was continuously interrupted by a higher priority task, which was then interrupted by a higher priority task, and so on and so forth. So how do we prevent thread starvation? Now, first of all, there's a few solutions that we can follow. One would be to use rate monotonic analysis to properly schedule tasks. We should be setting our high priority tasks that have the shortest execution time. We don't want tasks that are going to be running for long periods of time to be high priority because they're going to block all those lower priority tasks. So we want to make sure that we go through and make sure that each of these guys have the right amount of time to be able to get CPU time for some appropriate period of time. You can even occasionally see thread starvation if you have 2 tasks that have the same priority. A real-time operating system will have an option to do something called round-robin scheduling or time slicing. In round-robin, a thread will run till it completes before it lets the next thread start running its code. Or until the thread says, hey, I want to yield the CPU. That could be potentially dangerous depending on the engineers that actually design the software. So what you can do is instead select time slicing. And what will happen is that task 1 will start executing its code for the time slice. When the time slice is up, task 2 will then start executing its code. Then when the time slice is up again, it'll switch to whatever the next task is. They'll go round-robin style, but they get a little bit of CPU time in between so that they aren't completely starved of access to the CPU to run their code. A few other potential ways to avoid a thread starvation issue is avoid polling and delay techniques. So I shouldn't be continuously polling for something. I should try to use an interrupt to make my system event-driven. If my RTOS has something known as preemption threshold, that can be a way to also avoid thread starvation. This lets you set a priority, a minimum priority that a task needs to have in order to preempt a currently running task. And then there's also things like dynamic thread prioritization, where if a thread's been starved for a long period of time, maybe you change its priority on the fly. Generally, that's not a technique I recommend. It starts to get a little bit way too complicated and doesn't really offer good benefit. You're better off using a good RMA technique and then just monitoring how your system's actually executing. After we set up the Tracealyzer tool, I'm going to show you how we can actually get some of this timing information and start to zero in on some of maybe where we have issues in our system. But you can imagine if I go and trace a whole bunch of events, and then I'm looking through a trace like this, I could probably see, if I see long traces like this, it'll make me realize that, hey, you know what, there's probably some thread starvation going here. You could actually click on it and then discover what the latency time is for the task to get access to the CPU. Another common issue is going to be deadlock. Now, deadlock occurs when two tasks need to access two or more resources in order to proceed, but each task has only one resource. Now, as you can see here in this trace that I took of the code, what's happening here is that we have two different semaphores that need to be shared. The first semaphore is taken, so semaphore 2 is taken by one task. It starts executing its code for a while. Then a higher priority task comes and says, hey, I want semaphore 1. It also needs semaphore 2 in order to execute its code, and the other task needs semaphore 1. So now as soon as this higher priority task takes semaphore 1, these two tasks are in contention. Task A here tries to take the semaphore, except it's already owned by a different one, so now it's blocked. Now it's going to yield the CPU. As you can see here by this line, we got a lot of time here where this thread is just kind of waiting to execute. Now maybe this other task comes in, it tries to execute its code for a while, and then it says, hey, I need to get semaphore 1, except now it's blocked. So this task is dependent on a resource that this task has, and this task is dependent upon one that this task has. This is deadlock. Neither task can execute, and they just get stuck here, as you can see, where neither task is executing because it's waiting for something to happen. Obviously, this could be extraordinarily dangerous in a real-time embedded system. Now, there's a couple ways that we can avoid this from happening. First, any task that requires 2 or more resources, they should acquire those resources in the same order. So, for example, instead of this task getting semaphore 2 and then trying to get 1, and this one getting 1 and then trying to get 2, they should both try to get semaphore 2 followed by semaphore 1. This way, if one of them gets one of the resources and the other one preempts it, the second task won't try to get it. It'll just say, oh, I'm blocked. Okay, I'm not going to take the second one. And then the next task, the other task that needs it, will be able to acquire it, get its code done as fast as possible, and then release both resources. Alternatively, like in this example here, what we could do is set a timeout for the semaphore that says, hey, if I haven't received the semaphore in a certain period of time, I'm going to release it. One of the problems with this, while this is a great idea, you can see here that was actually implemented here. The semaphore is released here, but the problem is that it waited this long period of time here where this other task got blocked, and if it would have just not had that resource for that whole time, this other task could have completed well before this. So we're adding a whole lot of delays into our real-time performance, and we could really be seeing some of those other issues that we talked about where the system hangs up for a short period of time and then appears to recover. Probably one of the most heard of issues is priority inversion. Now, priority inversion occurs when a high priority task is blocked by a lower priority task. As you can see here in this trace data, what happens is that this task, this low priority task, starts executing. It takes a semaphore. It gets preempted by a higher priority task, which then tries to get that exact same semaphore. It becomes blocked, so we can see here that it's blocked here. A lower priority task starts executing, which has preempted this low priority task, which has the semaphore, the resource that this high priority task needs. It runs a completion before finally this low priority task gets to run, complete, give back the semaphore, and then you can see here our higher priority task is finally able to get access to that resource. The problem is it's the highest priority task. It should have been able to run this whole time, but instead it got delayed. Of course, very horrible, interesting things can happen to our system when a priority inversion occurs. We want to try to avoid them. There are several solutions to be able to solve or at least minimize the impact that a priority inversion will have on your system. First is to use a mutex with a priority inheritance mechanism. What this means is that if a low priority task blocks a higher priority task, this low priority, which has the mutex, its priority level will be elevated so it has the same priority as the highest as this priority task. So this will suddenly have the same priority as this. That way it can't get blocked by a task of lower priority than this. This will run to completion as quick as it can, and it will help minimize how long the highest priority task is impacted. So that's one way to go about doing this. The second is to just properly design and architect your tasks and your resources in your real-time application. You can use formal methods like rate monotonic analysis. At least create a model of how your system should behave, and then you can use trace tools to go back and verify and validate your model. Alright, so we've been talking about here are some of the possible issues we can have with our embedded system. What can we do to actually find and solve these problems? I have something on the bench, it's not working the way I expect it to. I need to get to the root cause, I need to get there as fast as I possibly can. The way that I can go about doing this is to use tracing tools. And the trace tool that we're going to look at today is actually the Percepio Tracealyzer tool. We're going to couple its behavior with the Keil MDK Microvision 5 that's going to be running RTX 5, which RTX 5 is a real-time operating system. So what's going to happen is that we're going to have our source code, we're going to have our RTX 5 RTOS, and what we're going to do is enable event tracing. So our code is, whenever an event is going to occur, it already has built in, it's instrumented to be able to put an event that occurs into a RAM buffer all these events will be stored in. And then when our trace tool says, hey, give me that data, maybe when our system doesn't have anything going on, it's in the idle task. So it says, hey, you know what, I've got some time where I'm doing nothing. Now let's send this trace buffer over and record that data so it can be viewed later. So what we end up doing is we're going to set up a trace recorder library along with the RTOS inside of an application, and then whenever something like a thread changes, so we go from maybe blinking a blue LED to blinking a green LED, or maybe we initialize a new thread in our system, that is where we're suddenly going to have an event occur, and that will be recorded. Now events can be anything that happens in an RTOS, so it could be creating a new task, giving a semaphore, taking a semaphore, locking a mutex, unlocking a mutex, sending data in a message queue, and the list goes on and on and on. But those are the types of examples of things that we're going to be able to take a look at. In order for this to be effective though, we need to actually set up the tools. So let's see how we can do that now. Let's take a look at how we can set up this project so that we can get an event recorder and actually start to see the data that's coming out of our system. Now the first thing you'll want to notice here is that we have an event recorder.h file that's going to be included in our system, provided that we have the RTE compiler event recorder option defined somewhere in our system. Now in order to get that option defined, what we want to do is open up, we want to manage the runtime environment, and we want to look under the compiler options. Now you can see here under compiler there's an option for an event recorder. Now I already have this checked, but what this does is you want to make sure that you check this option so that the event recording using the debug access port is enabled. Once you go through and click that, you click OK, and what you'll find is that you'll have this compiler option here on the left hand side in our project settings. If we go ahead and expand that, you'll see that we have event recorder.h and the event recorder.c. Now this is a configuration file. We can go ahead and open that. And what we can do is click on this configuration wizard tab at the bottom of the screen and then expand the event recorder, and you can see here that we can configure how we're going to record data. Now by default the number of records stored is actually only going to be 64. In most cases, if you're going to be using Percepio Tracealyzer, you really want to have at least 512 records being able to be stored, and given the microprocessor that we're using, we really in this case are going to use 1024. This is going to allow us to make sure that we have enough memory allocated to be able to store all the events that could happen in our system. Don't forget that we want to have a good sized buffer so that if a lot is going on in the system, we don't want to always be having to push this data off to the recorder. We want to be able to store it in a buffer, and then once the system kind of gets into an idle state, then we'll offload it. So if we run out of buffer space, then we end up missing events. Once we've made this modification, we'd actually save this file, and then we can go ahead and close it. Another option that we want to make sure is set is at the very bottom of our main function here. If we come in here, we can see here there's another option for if the RTE compiler event recorder is enabled. There's this option here, and there's a couple of parameters that get passed in this event recorder initialized. The first is the recording option, and then second, when we actually start recording. In this case, we want to record all events in the system, and we want it to start as soon as the system starts up. This will allow us to capture all the startup events as well. So that's all that we're going to need in our source code. RTX5 already has all the hooks inside of the kernel to be able to record different events inside the buffer for us. So at that point, we're actually set up and essentially ready to go. The only thing that we want to do is make sure that we configure our debugger properly. So if I open up the project options, go to the debugger, I want to make sure that I select the debugger that I'm using appropriately. In this case, I'm using a J-Link. I'm going to go to my settings, and you can see here that depending on the J-Link that you're using, if you loaded the J-Link software onto the K64 development board, then you would probably find that you would be running at a serial wire debugger at about 5 megahertz. If you're using an external J-Link, you might be running up to 50 megahertz. Using the onboard J-Link on the K64 Freedom board, you are going to find that the event data that's sent out is a little bit more on the a little bit slower than if you were using a high-end external debugger, but you will still be able to get trace data and at least see how these capabilities work. The other thing you want to do is probably make sure under trace that you enable the trace capabilities. So make sure that trace is enabled and that you set the core clock frequency to 120 megahertz. After that, the debugger set up, we can go ahead and click OK and close out of these settings. The final piece that we want to make sure that we set up is that we come over here to Edit and come under Configuration. In the Other tab, there's this UV SOC for TCP/IP settings. We want to enable this. And what this is going to do is it's going to stream the event data over TCP/IP to a server that then allows Percepio Tracealyzer to connect to the same port and get the streaming data, record it to a file, and then later on we'll be able to actually view our trace and see what was happening in our embedded system. Okay, let's now actually run our code. So this code has already been compiled, but just to make sure, we can go ahead and hit F7. You can see here at the bottom, no errors, no warnings. We're ready to actually run our code. I'm going to go ahead and load it onto the target. Now, one of the first things I'm going to do when I start setting up for event tracing is I'm going to want to come over here to the analysis window, pull it down, and look at the event recorder. So I'll go ahead and click on the event recorder. And what will happen is it will appear in the right-hand side here. Now, what I want to do first is I want to step through my code. You can see here we've got this, we just initialized the core clocks. And then when I call and step over this event record and initialize, I should see an event occur in my event recorder. Once I see that, you can see here I have an event that occurred, event 0, initialization event. This means that I do have my settings set up appropriately. And if I start running my code, I'm going to start getting events inside my IDE showing me that the system is running and executing. Now that I know that my system is set up appropriately in the code, I can actually come in here, open up Tracealyzer for Keil RTX5. I can click File, and I can connect to the ARM Keil IDE. This will bring up several windows that I can start taking a look at here. As you can see, there's not a whole lot going on, but because I already have my MDK already set up and ready to go, you can see here that it automatically connected. So if I wanted to, I could disconnect from Keil. I don't want to do that. Instead, what I'm going to do is I'm going to actually say Start Recording. And when I start recording, you can see here it connected to that TCP/IP port that was set up. And you can see here in live time here, the data streaming across. You can see the events coming through here in the raw event log window. We can see here the CPU utilization and load. We can see the different threads that are in the system that we created. And we can actually see here the CPU load as well. As you can see, most of the time, this system is unloaded. It's just sitting in the idle task. And only 0.01% of the time, it's in one of these other threads. So one of the things I can do is I could accumulate data as long as I needed to. I could run through my test cases, bombard the system, make sure that I put it through its paces. And then once I was happy with the amount of data that I wanted to collect, or maybe I have a problem I'm trying to debug, and once I create that issue and I see it occur on my system, I can then come through here and I can say stop. And once I stop here, I can say view trace. Now, when I view the trace, what's going to happen is I'm going to be shown this initial window here. And what I can do is I can see here that these are the tasks that are in my system. I have a startup, essentially a startup task. It really only occurs for a very short period of time while the system is initialized. I can see each of my threads, my blue, green, and red thread, and I can also see here this one on the left-hand side is actually my idle thread as well. So one of the things that we could do here is I could click on startup here. I can see this is where startup actually occurs at. It's way up here. Once I look at this on the right-hand side, it's going to provide me with actor information. So for example, there's only one instance of my startup code being executed, which is good because I don't expect my system to be restarting during execution. I can also come in here and see that the execution time was 130 microseconds to initialize the code. And then I can also see how much CPU usage it took. And there's even events that occur, and I can look at and see what those events are. So I can see here I initialized the kernel, I initialized the recorder, I see that there were some memory allocations from the system heap, I can see the exact size, and I can see that I created a new thread then from that allocation. And I could go through here and see all the events that occurred in startup. Now, if I wasn't using a real-time operating system, if we're thinking back to when you're using an 8-bit or 16-bit microcontroller, you don't get to see all this level of detail. Instead, what happens is you have to try to blink LEDs, you have to try to use printf messages, you have to try to figure out ways to let yourself know that, hey, something's happening to my system, but you don't necessarily know what it is. Using these tracing capabilities, though, we're not guessing what the microcontroller is doing or what lines of code it might be executing. We're seeing, essentially, these events are coming out. We're seeing what's being executed, at what time, how much memory is being allocated, and this gives us that fine level detail that we need as engineers to be able to see what our system is really doing, and it takes the guesswork out of our debugging. So let's take a look at another example here. As you can see that the code was actually executing here. If I zoom in, we can see that fairly quickly the blue thread started executing. And as we can see here, if I click on the blue thread, I see that in my trace, it actually occurred 75 times. I can get the typical execution time, so we can see here the lowest execution time, the quickest execution time was 11 microseconds. On average, it took 16 microseconds. The worst case during the execution time was 28 microseconds. Now, as a developer, this allows me to run my code, run through test cases, and then get real timing data on how long it took my threads to execute. We can find out what the typical response time is. What if I have a task or a thread that I expect to occur, to have a response that when it comes due, it's always going to respond within 1 millisecond. But I don't necessarily know that if I'm just running my code. I'm essentially guessing and hoping that that actually occurs. I could click on that particular thread, look at the response time, and make sure that worst case, that the highest response time does not exceed the actual requirements for the system of 1 millisecond. If it is over that, then I know that I could potentially have a problem with my code, and I need to go in and make some adjustments to it to make sure that I actually meet my timing deadlines. If I see that it is below that 1 millisecond mark, that allows me to realize that, hey, you know what? I went through all my worst case test cases, and the system is actually meeting the performance requirements that I expect out of the system. Now, looking at idle time and the different tasks and how long it takes them to actually execute isn't all that the Tracealyzer tool will show us. I can actually come in here and say that, hey, I want to look at some of these kernel objects. I want to look and see when semaphores are allocated and used. So you can see here that at this time, there's some requests to get a semaphore. And if I zoom out here, you can see at different areas where the threads are competing to get access to the semaphore. In this case, this one was blocked and it timed out forever. Here in green, we can see that the semaphore acquire call was successful. It was actually able to get it, and it tells us how long it took it to be able to get the semaphore. So you can imagine that you could come in here at the fine level detail and control and make sure that you don't have any issues occurring in your system, and that everything is doing exactly the way, it's behaving exactly the way you expect it to. Obviously, zooming out at a very high level, we can see all kinds of different events occurring, releasing semaphores, acquiring them. We could even click on some of these and see how they're actually behaving as well. Now, there are a lot of ways that we could analyze this data rather than just scrolling through and trying to manually look through the timing that's associated with our system. We can come up here to the view, and you can see here there's a lot of different views that we can look at. For example, I could look at the CPU load graph. This CPU load graph gives me the worst case that while my system was running, I can see when threads were executing and how much CPU load they were using. So you can see here's my startup. Here's the essential maximum load on the CPU was 0.12%. And then in typical executions here, we can see here Sometimes these tasks all align, but when they do, the CPU usage is still not that bad, 0.06%. If at some point I saw this spiking way up to like 99% or something like that, I know that there were some bottlenecks in my code, and I may need to go in and adjust the code so that I don't get those giant bottlenecks anymore. It really allows me to see how much CPU utilization I have, which will also come back if I'm trying to do a rate monotonic analysis and prove that my tasks can actually execute and meet their deadlines. This type of information can be a great way to go about validating the model that you put together at the beginning of your design. Another useful view is looking at the memory heap utilization. What this does is it opens a window that allows us to see how much heap memory is utilized over time. Now, in most of my applications, I always allocate from the heap space at the very beginning of the application during the system initialization. And at that point, I stop using the heap as much as possible. One of the reasons is that most applications or most implementations of malloc are actually non-deterministic. And if we're trying to create a deterministic application, then using malloc isn't going to be a great thing for us to use. So you can see here from this heap utilization graph, we start allocating memory here early on in the application. Probably when we're creating tasks, you can see, oh, here's another one, here's another one, here's another one, and over time we eventually initialize the whole system until we get to the maximum utilization, and then for the rest of the application we don't use the heap at all. But if we were creating and destroying objects, we could see this heap utilization and see, are we, how much heap space are we using over time? May even allow us to then go in and start to figure out, okay, is there a likelihood that I could be starting to get fragmentation if I'm using too much, where I'm creating and destroying objects? But this can give us another view into our system to see how we're utilizing memory. It can also be very useful to review the communication flow through the system. And the communication flow can be simply threads. It could be using message queues, it could be just using semaphores, for example. So I could come in here and say view, look at my communication flow. It's going to pop up a window for this application that looks like this. And what I can do is I can click on these objects and I can see where my semaphore, when was it received by what objects? When was it sent by an object? And I can see, okay, well, for this thread, how was it being used? Okay, here it was using this semaphore. And this can be extraordinarily useful. Now, this is a very simple example, but you can imagine that over a course of an application that's very complex, where threads are sharing multiple semaphores and mutexes and event flags, those types of things can become very difficult to discern how the communication behavior is going, how the flow of the application is. And using something like this allows you to see how that communication is being done inside the application. Another quick example of something that we can do is we can go through and get an actual report of everything that happened in our system. So I can grab a statistics report. The statistics report is going to allow me to select what actors I want to actually include in my report. In this case, I'm going to say that I want to show all of them. And what I'll get is a statistics report that looks very similar to this. And you can see here that it provides us with the date and the time and how much trace, how much data, and then it'll go through here and it'll give us some basic information. What were the priority levels of these different objects? How many times were they executed? What was their CPU utilization? The min, the average, the max timing. What was the fragmentation? What was the separation between different calls? So I could come in here and figure out, okay, between calls, if I wanted my task to run at 100 milliseconds, how close was I to actually hitting that particular value? If I discover, hey, I'm off, then you know what? Maybe I need to go and make some adjustments to my software so that I can actually meet the requirements. And then you can see here that it provides some other information like profiles for the actors, response time, execution times, you can see here are all in here. But you could go through and run a very complex application and come in and then examine this data. Whereas, as I mentioned before, normally what you would do is you'd run your program, run a few test cases, and pretty much cross your fingers and hope that the system's actually working the way you expect it to. Using a trace tool like this where we can record the events, we can uncross our fingers and actually examine the data in a very scientific and engineering way to validate that our system does what it's supposed to. And more importantly, if it doesn't do it, it allows us actually to dig into the details and try to figure out where potentially things could be going wrong. Once again, before, that was guesswork. We'd say, well, the system's not working. Okay, maybe it's this, maybe it's that, maybe it's some other thing. Instead, now we can actually run the system, take the trace data, and then go through and review the trace and see what's going on. Do we have a priority inversion, or, a semaphore is being held too long by somebody, or what's going on? We can actually start to see these details now, which can make us debug our systems far faster than we used to before. Now that we've seen how we can set up a trace tool and actually use it, I think it's probably pretty obvious how powerful this type of tool can be for us. One of the things that we really want to dig in and take a look at as well in this webinar before we conclude today is I want to talk a little bit about performing worst case stack analysis. We saw that we created a couple of tasks inside of our sample application, but we just used the default stack size. Using the default stack size, one, could lead to very inefficient use of memory, but it could also lead to stack overflows. So what we're going to do here is I just want to mention, a best practice for developing a real-time application is to perform a stack analysis on every single task in your system. Every task is going to have stack space allocated with it because it behaves like it's its own independent application. And sizing the task stack is not a one-size-fits-all endeavor. So we really have a couple of options available to us on how we can go through and calculate the maximum stack size. First, we could manually calculate it. We could pull out our code and start looking to see, okay, what's every function jump that we make, how many local variables are there, and so on and so forth. Option one, not terribly efficient, definitely prone to errors. The second, we can also go and perform a static code analysis. We can use something like PCLint, and it could go through and it will do all of that for us. Keep in mind though that the static code analyzer is not going to be able to detect if we have function pointers. So if I dereference a function pointer, most static code analyzers aren't going to take that into account, which means that my stack analysis, my worst case stack analysis, will actually be a little bit less than it should be. And then of course the third way is to actually perform experimentation under load using watermarks and RTOS aware debuggers. This is the technique that I'm going to show you right now using the Keil IDE. Before we dive into the details on how to perform a worst case stack analysis and fine tune our stack space for a thread, let's take a look at the example application that I put together. Now this application is going to be running on the K64 Freedom board, and we're really just going to be utilizing the LEDs on the board. So we have a tricolor LED that has a red, blue, and green LED all in a single package. 3 different threads in this example application. One is to control the red LED, one's to control the blue, one is to control the green, and then there's a semaphore that's then going to be able to be used to coordinate and synchronize these different tasks and have them work together to blink the LED. In order to actually use the threads that have been created, we need to create an attribute for each of those threads before calling OS Thread New API that's part of RTX5. So what I've done here is I've created an attribute for each of the different threads, and I've done it in a slightly different way. So you can see here for the blue thread attributes, I've provided a name of blue thread, I've given it a stack size of 256, and I've set the priority level to OS priority high 1. I've set each of these threads to have the exact same priority level, and the first 2 threads, the green and the blue, I've set to have a stack size of 256, while the red thread I set up to stack in a slightly different manner. Instead what I did was I actually allocated an array, which is then being assigned to the stack memory here, as you can see, and then other than that, the stack size is set by just taking the size of whatever the thread stack happens to be. Now these attributes are used by OS Thread New. We're going to actually pass them into the initialization function to create our thread. And you can see that here in the main function. We call a clock initialization, then we initialize our LEDs, we call OS kernel initialize. This is actually going to get the RTOS up and running. Then once it's been initialized, we're going to create each thread. So I make a call to OS Thread New, pass in the function that I want to be executed as part of the thread, and then I'm going to pass in a pointer to the attributes. So for the blue thread, I'm going to pass in the blue thread attributes. For the red thread, pass in the red thread attributes, so on and so forth. Now, as you can imagine, when you first create these threads, we have no clue what to expect as far as stack size goes. So what we do is we usually either use the default stack size or we assign a value like I did in these, where I set the value to maybe 256. But in order to actually figure out what the worst case analysis is, and I can do this by dynamically running my code, running test cases, and then there's a neat trick I can follow within the IDE to actually see what percentage of the stack I'm using. So let's take a look at that now. So what I'm going to do here is I'm going to actually execute my code. Once the application has been loaded, I'm going to want to perform a worst case stack analysis. So what I'm going to do is I'm actually going to come over here, I'm going to say run the code. And the code is going to start running and executing and doing everything that it's supposed to do. And what I want to do is now run all my test cases. I want to throw as many events as I can at the system, make it do what it's supposed to, and try to make it follow the worst case that it could possibly ever have thrown at it from a user. And once that's happened, then what I'm going to do is I'm going to actually stop executing the code. I'm going to come to View. I'm going to come down to the Watch window, and I want to look at the RTX RTOS watch. And what this is going to do is on the right hand side of the screen, it's going to open up a watch window that's going to allow me to see what's happening in the system. And what I can do here, you can see there's an option here for threads. We can expand that and take a look at the different threads in our system. You can see here that we have an OS RTX idle thread. We have our blue, red, and our green threads. Now, if I want to, I can go ahead and open this here, and I see that there's different parameters. The state of this particular thread is currently blocked. I can see its priority. I can see its attributes as well. I can also see, okay, it's waiting. It has a semaphore that's waiting for, that's set to OS wait forever. So I can get some very useful information here about how the RTOS is actually working. And even more importantly, in order to perform that worst case stack analysis in a dynamic manner with the code running, we can see here that there's a stack size here, and it's saying that it's currently 34% used, and I'm using 88 bytes of the stack space. If I expand this out here, I can see also exactly where the stack is located at. In this case, the top side of it is at hex 200,000 and 160. I can see that the size of it's 256. There aren't any flags. But most importantly, I can see here that in order to blink the LEDs as part of this blue thread and control the semaphore, I've probably really oversized my stack here by quite a bit if I'm only using 34%. So that means that that value of 256 bytes is probably way too much. So I could go back and maybe reset it to something like 128 bytes instead. I could have that. And then really what I want to do when I'm performing worst case stack analysis is I want to know what the worst stack usage is, and then I want to maybe adjust it by as much as 1.5 times however much stack space is being used. Now that's a rule of thumb, of course. It depends on what the particular thread is actually doing, but it gives you a general idea. If I wanted to, I could also come in here. I could see, okay, what's the usage of, you know, the idle thread. The idle thread really isn't doing anything in this application, so it shouldn't be using any stack. I can come in here and look at the red size here. Well, you can see here, well, the red stack is only using 17%. Why is that? Well, if you remember, I went through and I created an array of 64-bit data locations, and I created 64 of them. So I actually have 512 bytes of memory allocated to this particular thread, which is definitely way too much if I'm using 17%. So then, now that I've gone through and I've seen what these different threads use, I can go back and make an adjustment to each of these threads, and I can tune it so that I'm not using too much RAM for any particular application. All right, a few more general best practices for you to think about as you design your real-time applications. We've talked about how we can set up a trace tool, how we can perform a worst-case stack analysis. Obviously, those things, they take a little bit of getting used to, and it's something I expect that you'll be starting to do in your development cycle. But before we close, let's talk about a few other things that you should probably be doing when you're designing your RTOS-based applications. One, you should always be using rate monotonic analysis, at least as a starting point for your task scheduling. You can come up with a model, figure out the approximate priorities for your tasks, and then you can follow it up using actual data from a trace tool by recording those events and seeing whether your model makes sense. If it doesn't, make changes to it, adjust the priorities, but at least allows you to validate the way that your system is behaving now, rather than just crossing our fingers like I've mentioned before. We want to make use of priority inheritance in mutexes. So if we have a shared resource that we're going to use, we need to have mutual exclusion for, use a mutex. Don't use a binary semaphore. When you have two or more resources that are required, acquire them in the same order. By doing this will help prevent deadlock inside of our system. A lot of OSs will also have a lot of real-time operating systems will have a default stack depth that is usually probably too small for any given task. A rough rule of thumb is to start with hex 400 for the size of it, but you really got to look at your task and see what you're doing. If I'm blinking an LED, 256 bytes of stack space is just going to be way too much. But if I'm running a USB stack, starting with just a kilobyte isn't going to make any sense. I probably want to start with 2 kilobytes worth of stack space. So, start out with a best guess from experience, but follow it up by performing that worst case stack analysis under load to actually see what's being used in the system. I want to thank all of you for attending today's webinar. I hope that you've found it as interesting as I have. I think debugging is a very important, critical skill for us as embedded software developers. And from the developers I've talked with, we just don't pay enough attention to it. A lot of us are spending 40 to 80% of our development cycles debugging software rather than designing and creating new things. So as you start to think about this, definitely download the tools, understand how they work, and start using them to validate your own assumptions. Once again, we are engineers. We're data-driven. Developing software and then running it and just trying to look at a black box and make sure that it behaves outwardly the way that we expect it to, that's not really a way to prove that our system works the way that it's supposed to. And using tracing tools really allow us to understand more of how the software is behaving and get to the level of detail that we need to not just be comfortable that our system works properly, but debug issues when they actually occur. If you could cut your debugging time in half, as we were talking, if you spend 40% of your time debugging, you might be able to save 2 months in your development cycle. Add that up, that ends up being quite a bit of cost, but also could allow you to get to market just before a competitor does and maybe get a much larger market share. Once again, thanks for your time and attention today, and I'll be sticking around to answer any questions you have about embedded systems or on how you can debug real-time operating system-based applications. Thanks.